Hey everyone, and welcome to The Explainer. Today, we're going really, really small, down into the tiny, kinda weird, and absolutely essential world of the atom. We're going to unpack its invisible blueprint, something called quantum numbers. These are basically the rules that keep the entire universe, well, orderly. So let's jump right in.
So to get our heads around this, let's start with a pretty simple question. We all know atoms have electrons whizzing around, right? But where exactly are they? I mean, it's not like you can mail them a letter, but what if they did have some kind of unique, specific address?
Well, it turns out they totally do. And that address is described by a set of 4 quantum numbers. Together, these 4 numbers give us a complete picture of an electron's energy and its most likely location in an atom. And here's the key. No 2 electrons in the same atom can have the exact same 4 numbers. It's like a cosmic law that keeps everything in its proper place.
All right, so let's break this address down piece by piece. We'll start with the biggest, most general part of it, the energy level. We call this N, and you can think of it as the street the electron lives on.
This first number, the principal quantum number, or N, tells us which main energy shell the electron is in. It's the broadest part of the address, kind of like the zip code or the city. It gives us a sense of the orbital's overall size and how far, on average, it is from the atom's center, the nucleus.
And the rules for N are actually pretty straightforward. It can be any positive whole number, so 1, 2, 3, and on. And it's simple. The higher the N value, the bigger the orbital. That means the electron has more energy and is hanging out further away from the nucleus. An electron on street number 3 is just more energetic and further out than one on street number 1. Simple as that?
Okay, so we've got the street. Now what about the type of house it is? That brings us to our second quantum number, L.
This one's called the azimuthal quantum number, or just L for short. And its job is to define the actual shape of the orbital where the electron is. So if N is the street, L tells us if the house is a simple sphere, or maybe something a bit more complex, like a dumbbell shape. It's all about the geometry.
Now, chemists have a shorthand for these shapes. An L value of 0 gives us a simple, spherical s orbital. An L value of 1 gives us a dumbbell-shaped p orbital. And as the numbers get bigger, the shapes get even more complex, and we call them d and f orbital.
But here's a really critical rule. The type of house you can have depends on the street you're on. The value L is limited by n. It can be any whole number from 0 all the way up to n minus 1. So on street 1, where n is 1, you can only have L equals 0. Only spherical S houses are allowed. But once you get to street 2, where n equals 2, you can have L equals 0 or L equals 1, meaning you get both S and P-type houses. See how it builds?
All right, we've got the street and the house type. Now we've got to find the specific room inside the house, and that's the job of our third quantum number.
This is the magnetic quantum number. We write it as m sub L. This number tells us how that orbital is oriented in 3D space. You know, if that p orbital is a dumbbell shape, is it pointing up and down along the z-axis, or is it horizontal along the x or y-axis? M sub L nails down that exact orientation. It's the specific room in the house.
So let's run through a quick example to see how this works. Let's take a p orbital. We already know from before that its house type is defined by an L value of 1. Okay, now for the rule to find all the possible rooms, the m sub L values. It's super simple. It's just every integer from negative L to positive L. So since L is 1 for our p orbital, the possible values are just -1, 0, and +1.
So, that's it. 3 possible values. What does that actually mean for the atom, though?
It means that a p subshell isn't just one thing. It's actually a set of 3 distinct orbitals, each one with its own unique orientation in space. And each of those 3 rooms can hold up to 2 electrons.
Street, house, room. We've got the complete location pinned down. But the address has one last, super important part. And this one isn't about location at all. It's about the resident itself.
And that is the spin quantum number, or m sub s. This describes a fundamental property of the electron itself. We often call it spin. You can kind of picture it like a tiny little spinning top that can only spin in one of 2 opposite directions.
And there are only 2 options here. That's it. We call them spin up, which has a value of +1/2, and spin down, with a value of -1/2. This is the final, crucial piece of the address. It means that if 2 electrons are going to share the same orbital, the same room, they absolutely must have opposite spins. This is what guarantees that every single electron has its own unique quantum address.
Okay, let's take a step back and look at the whole system working together. We've gone from the street, to the house, to the room, and finally to the occupant in that room. Let's see how this builds the entire structure of an atom.
Take a look at this table. It really lays it all out. Let's look at the row for the second energy level, where n equals 2. Remember our rule? That means L can be either 0 or 1. That gives us a spherical S subshell and a dumbbell P subshell on that energy level. Now the S subshell has just one orbital, but the P subshell has 3. And since every single orbital can hold 2 electrons, the whole n equals 2 level can hold a total of 8 electrons, each one with a perfectly unique 4-number address. It all fits together.
So let's just recap our address analogy one last time. N is the street, the overall energy level. L is the type of house, the orbital shape. M sub L is the specific room in the house, the orbital's orientation in space. And finally, M sub S is the occupant itself, defined by its unique spin.
And here is the real reason this all matters. This whole address system isn't just some abstract theory for physicists. It is the fundamental rulebook for all of chemistry. These numbers and their rules dictate exactly how atoms can bond together, what kinds of molecules can exist, and they are the deep underlying reason why the periodic table has that iconic shape we all recognize.
It's an unbelievably powerful and elegant idea, right? But it does leave us with a pretty fascinating question to chew on. If every electron has its own fixed address based on its energy, what does it actually mean when an electron absorbs some energy and moves? What happens when it jumps from one address to a completely different one? Well, that's a great story for another explainer. Thanks for tuning in.